Welcome, everyone. Welcome, YouTube. We are back for another water, wetlands, and watershed seminar. So thank you very much for braving the rain and coming out to see us. So good now. Come on in. Yes, come on in. Welcome. All right. So it is my great honor today to introduce our speaker this week. So we have with us Dr. Osama Tech. Osama is well, did you write your own bio? It says he's a dedicated researcher. Which I can definitely, I can agree with. I've been very lucky to work with Osama for a while through a jointly funded project by the Army Corps of Engineers and Osama's advisor at USF, Mauricio Arias. So we met maybe close to 4 years ago now, 3 or 4 years ago, and I've had a very collaboration and collegial relationship. So thank you for coming up, Osama. He's currently a postdoctoral scholar at USF, where his research focuses on hydrology and water quality. And in particular, he's been working on methods to optimize this very challenge. Does anyone, let's see, is it in the title? No. Anyone know what this lake is? Lake Okeechobee. Lake Okeechobee, right? Is it right? Yeah. Right. So we're going to hear a lot about Lake Okeechobee. And he's been working for a long time to understand how previous management of the watersheds that drain into the lake have caused water quality issues. And now that it's such a tightly constrained system, how we can better manage perhaps with less ecological harm, especially to the estuaries that it sometimes feeds out to. So Osama has his PhD in civil and environmental engineering from USF. And before joining USF, he was an assistant lecturer in the Department of Irrigation and Hydraulics at Cairo University. And that's where he got his master's degree in hydrology and water resources engineering. So he's on the job market, he's getting the interviews, he's getting the calls. So if you're watching this online and you see Dr. Tarabe's talk and you want to throw an offer his way, do it. He's ready to take one. So floor is yours, Osama. Thank you for coming
Thank you, David, for this nice introduction. Thank you for inviting me. It's an honor to be invited to speak here at the prestigious UF Water and Wetlands Seminar. And yeah, today I am presenting part of my work on this Lake Okeechobee in South Florida about optimizing the lake operations to improve water quality in the downstream waters from the lake. So let's get started. So yeah, that's like the outline of the presentation. I'll go through some background about the problem there and the objectives of the study. And then I will take some time to speak more about the algal blooms and Lake Okeechobee system. And then I'll go through the methods we do to get this work done, and then some promising results, and finally we'll conclude and we'll have some time for questions for sure. So yeah, that is start with this photo from one of our lakes at the Lake Okeechobee system. You can see this water is very green, and you can smell it from here, right? So yeah, that's algae. So mainly how algae develops. So eutrophication, because of agricultural and urban activities, lead to those eutrophication of water, and eutrophication come together with warm water temperatures. Those cause the algae to develop, phytoplankton to grow. And then with phytoplankton grow more, it turns into algae blooms. And those algae blooms, if you don't know, they cause a lot of environmental problems. They disturb the ecosystem functions. Algae depletes oxygen, and it blocks sunlight from penetrating into the water, so that affects, of course, the aquatic species, and then also affects human, of course affects the water sources for drink, domestic water, irrigation water. Of course affects the recreational activities, fisheries. So it's a really big problem, and we see this problem a lot in the Lake Okeechobee. We'll talk about this later, but yeah, that's the problem we're talking about today. So moving forward to focus on the drivers of algae in order to trying to mitigate that algae bloom problem, we'll focus on what drives algae. So this diagram here is a nice illustration of the drivers of algae. So the first thing is the nutrients. That's a major driver of algae, and like mainly phosphorus and nitrogen from both agricultural activities, urban activities. So those agricultural and urban runoff carries tons and tons of phosphorus and nitrogen, flows eventually into the water. So nutrients, as well as sunlight, like that, the other factor, availability of sunlight, and like this warm water. So those leads to the phytoplankton growth. And as I mentioned, like with excessive phosphorus and nitrogen, so like phytoplankton is an abnormal, what to say, like a normal phenomenon to happen. But when excessive nutrients happen, like this algae like blooms, and then we have those algae blooms, and then those algae blooms usually release toxins to the water, and that's when it becomes like harmful algal bloom, like HABs, we call it HABs. So that's when the problem happens. So yeah, our problem is the regular occurrence of those algal blooms that affects both the ecosystem and the humans. So there are, of course, several approaches trying to remove or reduce those algae blooms from the water. So this one here, this folk here is trying to harvest the algae from the water, and that's like physical technique to remove algae from the water. But think about Lake Okeechobee, it's huge, like very huge. So that will not be practical at all. Take him like years. Then here they are using chemical components to do those chemical compounds with algae, and then this algae will settle down. But also it's not practical and it's very cost effective. Speaking about large area like water bodies like Lake Okeechobee. And finally, this here is like biological processes. Like this guy here is providing algaecide to the water, but same problem. It's not very efficient. So that's why we not me, but like the scientific community, we thought about this new technique. It's not still like not very new, but like it's novel, still novel, to design operations or releases from the water body to improve the water quality within the lake itself, or the water body, any water body. So discharge releases from the water body, like it affects nutrient cycling within the water body. It affects like the algae dynamics. So it could be a way to reduce the algae and improve the water quality. And those releases going to the downstream waters. So if we can control those, we can reduce, of course, like the nutrients and phytoplankton discharges with the water to the downstream waters, and then we can improve water quality in the downstream. So that's very cost effective, cost effective and very environmental friendly technique. So moving forward, moving forward to focus on the Lake Okeechobee. So before I start in that, so yeah, we have a problem, which is algae bloom. Even before we talk about the lake, algae bloom is a problem everywhere. And then we have this hypothesis of designing those water releases to improve water quality within the water body itself, and also talking about the downstream waters. So let's now focus on the Lake Okeechobee itself. So for you who doesn't know Lake Okeechobee, So, yeah, sorry, I should put Gainesville somewhere here.
It's okay.
Yeah. So
We're small enough.
Tampa's
so-
here.
Yeah.
And then, yeah, that's Lake Okeechobee in the South Florida. And then this lake is very large in area, surface areas like 1,700 kilometers square. And it's the second largest lake by surface area in the United States. And then, however, it's very shallow, like the average depth is just 2.7 meters. So it's very shallow. And it's very crucial to the South Florida system here. So it provides water for different users, for domestic uses, and for this green area, that's the Everglades agricultural area. And it's a target for recreational activities and fisheries. And of course, it protects the surrounding area from flood risk. And then it also sends essential waters, fresh water to some critical systems like this San Lucie estuary here to the east and the Caloosahatchee estuary to the west. And of course, it sends water also to the Everglades. Of course, many of you, of course, heard about Everglades. So, and yeah, not to forget also the lake itself is like an critical ecosystem, like it includes many different species. So that's the lake. So what's happening in Lake Okeechobee? So yeah. So here, the lake receives tons and tons of phosphorus and nitrogen loads from its vast area watershed to the north of the lake. And you can see here, those are like the dominant land uses in this watershed, and like the most dominant land use like this pasture. So many dairies there release like tons and tons of nutrients to the lake. So for algae, as we mentioned at the beginning, like nutrients and warm water temperature. So nutrients is not a problem now, like there are excess nutrients. And actually, in addition to that, the lake itself, the bed sediment of the lake, it contains tons of legacy phosphorus. And this figure here illustrates like the bed sediment total phosphorus in milligram per kilogram over the years. So also like, even if like this export of phosphorus and nitrogen here like did not or does not exist, still the lake itself is source of phosphorus. So yeah, nutrients are not a problem for algae now, okay? And yeah, warm temperature, man, that's Florida, right? So like it's always warm. So also like sunlight and sunny state, right? And sunlight, so the algae is like doesn't have any problem here. So that's like when we see all of those harmful algal blooms in Lake Okeechobee like every year. And that's the problem. So our problem now is the algae bloom in Lake Okeechobee. And furthermore, the lake discharges most of its water to the Atlantic through this San Lucie Canal and to the Gulf of Mexico through this Caloosahatchee River, and some water still goes to the south of the Everglades. And so this pollutant water is discharged into the estuaries, causing problems there for both the ecosystem and the communities there. And we are not happy with that. And this figure here, that's so the lake is operated. It's just like it's a lake already, but like it's confined with this dike that has control structures. So it's operated by the Army Corps of Engineers and the South Florida Water Management District through these operation rules. So this figure here, that's like the most recent operations in the lake. We call it like Blossom Lake Okeechobee System Manual. And like very quick, this here, that's the water level of the lake. And zone A is like the emergency zone. So if water level exceeds that, like release everything, release maximum water. And from zone B, C, and zone D, those are like the operational zones, like water level within those zones, like they release a specific amount of water to them based on like other factors, maybe some water supply needs or some ecosystem needs. And then finally, this water shortage management zone, that's when like they do not want to release water unless it's very necessary. Okay. So yeah, I wanna end the introduction with this figure here. That's like the ecological envelope in Lake Okeechobee. And for you who doesn't know that ecological envelope, so this grayish water level, so that's also water level, right? And this grayish range, that's they call it the ecological envelope, and this like the range of water level, the managers of the lake want to keep the water within if they can, right? And that's to maintain like the ecosystem habitat within the lake. So if the water goes above this ecological envelope, like it floods the aquatic vegetation within the lake, and it causes problems to those aquatic vegetation, and of course it causes problems to wading birds and other species. And then if the water goes below, so this aquatic vegetation still have problem dry out. Yeah, so they are trying to maintain the water within this water level, and this we call the ecological envelope. And you can see those are different years, and they are doing their best, right? But it's not easy. There are other factors. So yeah, so then yeah, to wrap up before I start the method. So yeah, the problem, the algae blooms in the lake, those algae blooms discharged to Lake Okeechobee and San Lucie. And our objective goal is to reduce the drivers of those algae blooms in the downstream waters by reducing the loads of those phosphorus, nitrate-nitrogen, and phytoplankton from the lake to the estuaries. And we focus on the summer month. So continue. So the method is very simple. Yeah. First, we need to simulate the water balance in the lake, water level and the discharges, right? And then we need to simulate the water quality dynamics in the lake, phosphorus, nitrate-nitrogen, phytoplankton dynamics. And finally, we'll try to design those optimal water releases from the lake to Lake Okeechobee and San Lucie to reduce those algae drivers in those downstream. So, in order to simulate the hydrodynamics in the lake, I developed this model. We call it LONI, Lake Operation Optimization of Nutrient Exports. And this model was like applied specifically to Lake Okeechobee. And in this model, it integrates 3 modules. Hydrologic module simulates the water balance in the lake. Water quality module simulates different water quality parameters in the lake. And finally, it includes an optimization engine that design those optimal releases we'll talk about later. And then this figure here illustrates like the application of the model to Lake Okeechobee. So those are inputs to the model: rainfall, evaporation, inflows, and some outflows are inputs. The flows to the south, we did not simulate those. We include those as inputs. And then what LONI simulates is those regulated flows to the Lake Okeechobee and San Lucie, as well as the water supply. So the water quality, yeah, we included 3 main parameters. Phosphorus, you can see here that's like the phosphorus, like conceptual model of phosphorus in Lake Okeechobee. And given it's a very shallow lake, so like, and given it has legacy phosphorus, so this bed sediment phosphorus is very important to include in the model, and that's why we like include it in our model, like the phosphorus resuspension from the bed sediment and phosphorus settling from water column to the bed sediment. So we include this settling resuspension criteria. And nitrate-nitrite, we simulated nitrate-nitrite being the plant storage. It's a little bit word. So
You didn't text and say you got here safely, right?
I did.
You did? Okay, all right.
We've got problem. So nitrate-nitrite, we simulate that as well because it's like the main nitrogen component that is phytoplankton uptake from the water to grow. So we simulate like nitrification, denitrification process, atmospheric deposition. We did not simulate it, but like it's an input to the models. And we simulate like the phytoplankton uptake from nitrate-nitrite, and then also like the release settling with the sediment. And finally, we simulate phytoplankton dynamics in the lake, including, of course, this uptake, respiration with nutrients, and the decay of phytoplankton, and the release settling with the sediment as well. And finally, the optimization. So we did not create an optimization engine, but we utilized a package that is already there called Platypus. That's like a multi-objective evolutionary algorithm optimization engine. And yeah, if I didn't mention, so this Luna model, I developed it within Python. So this package is Python package. And that's the optimization model for the lake. So that's the objective functions to minimize the constituent loads to Caloosahatchee and San Lucie, and to minimize water demand deficits. And by water demand deficits, it's like water demand minus water supply, right? And the decision variables were the monthly water discharges to Caloosahatchee and San Lucie. And then of course, there are some constraints, which are like the lake water level, like maximum, minimum water levels, and the maximum capacity of the control water structure. Yeah, also still in the optimization, I propose to do 4 optimization scenarios. So algae blooms occur in the summer month, because that's when the water is warm. So that's why I considered the summer loads. So I considered reducing the summer loads, like phosphorus, nitrogen, and phytoplankton loads during summer. So that's like the objective function in this scenario. And then all the scenarios, like it's this scenario plus. So scenario 2 is the same as scenario 1, but plus water temperature. So I just added so water temperature as a factor, because we found that algae blooms usually occur when water temperature exceeds 25 degrees Celsius, very high. So I included that as a factor in the optimization scenarios. And you remember this ecological envelope we talked about? I included as like a constraint, but like in the optimization, we call it like soft constraint, yeah, because it comes after. So the model will try to do that, and if not, we'll try to do that. So it's not the first constraint in the optimization model. And then the 4th scenario was to include those discharges to the south as a variable. So at the beginning, those were just inputs to the model. So I included them in this scenario as another decision variable, extra decision variable. So here we go, the nice part and the results. So start with the model calibration. So I calibrated the model for water and water quality. So here, that's like the water balance calibration. So here you can see this dashed represents like the simulated water level in the lake, and this solid blue is like the observed water level. You can see like the model did great in matching those observations with R squared of 0.9, and then it did not do as good for discharges to the Kalushachi and San Lucy. But that's because mainly those systems are very human like controlled. So it doesn't follow the rules usually, like it's very human controlled. Yeah. So water quality. So here we have phosphorus, nitrate-nitrite, and chlorophyll A. I use chlorophyll A as an indicator of phytoplankton. So overall, like for all the three constituents, like the model succeeded to like follow the trend. So first of all, yeah, this range that's like the observed range. So that's we simulated daily, but I calibrated monthly. So those are monthly values. So I use like the minimum and maximum values, and there are for observation there are 7 stations in Lake Okeechobee. So also I use like those all of those stations. Also like it's like they measure each 2 weeks. So I use like so we have some like lots of observations. So I use like the minimum and maximum to get this range. And then yeah, and then of course, as I mentioned, like we simulated daily, but we calibrated monthly. So this also like we have also a simulated range. That's fine. And like yeah, the model is very simple. And so like to get like an R square of 0.5 phosphorus, that's good. That's good. 0.57 for nitrate-nitrite. Not so good for phytoplankton, but that's very complicated. So yeah, we were satisfied with this performance because the model will be used for optimization. For optimization, we need to run the model like thousands of times. So we need the model to be very quick. So yeah, we accepted that. So here are like those optimal discharges. So that's discharges from the lake to the Kalushachi. And you remember we have those 4 different scenarios, right? So the 4 colors, like the blue, green, red, and purple, those 4 scenarios. This black is the baseline scenario, which is like the previous operation rules of the lake. And this gray is the current implemented. They just implemented that a few months ago, right? So that's why like the currently implemented operations. So those, of course, are monthly discharges. Easy to see, right? So those are monthly discharges for baseline, currently implemented scenario 1, 2, 3, 4. You can see that, for example, scenario 1 here targets like minimizing flows during the summer, right? And same here for scenario 3, because scenario 2. For scenario 3, which includes like the ecological envelope, like it's different because the model tried to get into this ecological envelope. And scenario 4, that was like sending more like including the water source and decision variables. Yeah, that doesn't follow any specific criteria. So, anyways, this beautiful graph here. So, the outer circle is the baseline, okay, and then we have the annual phosphorus loads, annual nitrate loads, and annual phytoplankton loads. And then here we have the summer phosphorus, nitrate, and phytoplankton. And then the shapes inside represent the scenarios. So the gray is this currently implemented scenario. And if you can see here, for example, here, that means that currently implemented, that's like 0.65. That means the loads are 0.65 of the baseline. So there's like a 35% reduction.
So if you're on the outside of the circle, that's as much load as used to be going.
Yeah.
And if you were all the way to nothing, it would mean everything is reduced to nothing.
Yeah.
So the further in you go, the better it is at
Exactly.
reducing the loads.
The
on each of
smaller
those, yeah.
the circle, the better the scenario, and the more the reduction. Thank you, David.
This graph is like the culmination of
many years.
Yeah.
So that's the one, yeah.
So yeah, we can see here that those blue and green, like scenario 1 and 2, focusing on the summer loads and targeting like the warm temperature, like they match, and they succeeded to reduce summer loads a lot, like 70% reduction in phosphorus and nitrate and phytoplankton, right? So a significant reduction. And I'd like to mention that you remember those water demand deficit, like was not heavily affected. I will come back to that later. So yeah, so overall, yeah, these like those optimal scenarios, specifically scenario 1, 2, succeeded to reduce loads very well. And that's San Lucy. So actually, like San Lucy, they were trying to reduce water and, like, of course, the related loads for years now. So that's why, like, you can see that our scenarios did not exceed the currently implemented a lot. So this grades like the currently implemented operation. Our scenarios, like, they kind of match at some point and kind of better, and some scenarios were even worse than in terms of loads than the currently implemented last one. But they focused on the San Lucy, not both. So here we're trying to do like the balance between the Osage and San Lucy. And yeah, so also yeah, we maybe scenario 1 and 2 also were like the best scenarios with San Lucy as well, and that's a good sign. Like have the same alternatives that succeeded to reduce all the different loads to San Luis and Caloosahatchee while not affecting the water demand, the water supply to the users. And that's like the water demand deficits image. And I just created this figure yesterday, so it's not perfect, but like, yeah, that's like also better than a table, right? So the baseline, actually, like the baseline still have water demand deficits, like they did not succeed to fulfill the water user requirements. With water, there is like this 18,000 acre feet per year. And implementing the new operation that will reduce this water demand deficit, like that's better for water users by like 26%. There's still be some deficits. Scenario 1, you can see like just like 4% increase in water demand deficit, which also like may be accepted given the reduction in loads that this scenario will implement. And then you see scenario 2, like it's more than 20%. So of course we'll go for scenario 1. And then scenario 3, there is actually like a reduction in water demand deficits, but like scenario 3, like increases not increases, like it reduces the loads, but not as well as scenario 1. Scenario 4, like see like 24%. And that's the beauty of optimization. Those like trade-offs, right? So we do trade-offs between water demand deficits and water quality parameters. So you propose solutions to the managers and they choose whatever they think would be better for the system and for the society. So yeah, that's the impact on water levels in the lake. So this yellowish, that's the same ecological envelope, and that's the baseline average year. And so that's not a specific year, that's the average of 16 years. And then this same gray is the loss on currently implemented, and those four are the 4 scenarios. And yeah, you can see that like water levels will compete with, like, because if you want to reduce the discharges, so you will keep the water in the lake, right, for some time, and then that's when like it competes with the objective function. So that's why we get like higher water levels, but it's still like it's within the same range as the currently implemented simulation, even it's better here, but it did not fulfill the ecological envelope. But also, given that that's average year, so maybe for some years it did succeed. So yeah, to conclude, so yeah, we presented a multi-objective optimization to design lake operation to minimize phosphorus, nitrate, and phytoplankton. We succeeded to produce some optimized releases that could reduce phosphorus, nitrate, and phytoplankton to both the Caloosahatchee and San Lucie, with some like reductions, 82%. But of course, that came at the cost of some water demand deficits and water levels. And yeah, then yeah, those scenarios 1 and 2, those targets like summer loads and the warm temperatures proved to be the best alternatives according to our point of view. The equal message, yeah, optimal reservoir operation strategies would offer efficient and cost-effective alternative to improve water quality in downstream water bodies while still meeting like water societal needs. Yeah, thank you.
Excellent, thanks, Osama. So we have time for questions. We have about 10 minutes for questions, so we'll start in the room. Questions for Dr. Tyler?
So, what model would you use for the predictions?
Yeah, as I mentioned, that model I developed. It's like a Python model, so I use like the equations that describe the water balance, the phosphorus, nitrate-nitrogen, process, nitrification, denitrification, all the equations that describe those processes, and I write like I wrote the code of this model.
So it was a model in one of the packages of Python?
No, I developed it from scratch. The only model that's my model.
That's your third baby.
Yeah.
How long do you think, an imaginary number, it would take to develop the operational guides to run under this new system, these new scenarios? From now to implementation.
Years. So, yeah, I believe it's not up to me, right?
Well, how long did it take for some Losum to go from Lorazolate to Losum?
16 years.
Say 10 years?
Interesting. So yeah, this laws like the baseline was like 2008. The currently implemented is just like few months, 16 years.
So the things you're trying to optimize was NOx, phosphorus, and phytoplankton. In that trifecta of optimization, if say for instance you're trying to minimize NOx, does that have a recursive property on HABs or on phytoplankton, the phytoplankton optimization? In other words, like, does that, because NOx, I assume, is one of the parameters within that model.
Yeah.
By optimizing that value, does that also play into the value of the percent of optimization of phytoplankton modeling? Or are those totally
Yeah, no, they are
Okay.
related, like it's coupled, like because if I understand well your question next, so that like of course NOx not right, it's phytoplankton uptake, like we use that as foil to grow, right? And then so phytoplankton grow, this NOx goes down, and if NOx goes up, like phytoplankton will start like uptake from that. So they are connected, the same as for phosphorus. So yeah, I model those as integrated parameters, so they affect each other.
How do you envision a manager actually using this? What do you think are the timescale needed for measuring, observing, and then deciding what to do?
For managing. Uh. I give like. Years.
But they don't have a year to make a decision, right?
They're
So,
sitting there in their office, they've got a nice window, they can look out on the lake, they can see the door algae. When do they decide, okay, let's check on the nitrogen and phosphorus and the algae, and then we'll decide we gotta go.
Yeah, okay, I misunderstand your question. So yeah, that like, I believe, actually, what really happens is they do that on weekly basis.
Mhm.
So and we are trying, so we are in connection with those, managers.
Mhm.
So we are trying to provide them with a week ahead. To cast those nitrate, phosphorus, phytoplankton, a week ahead
Mhm.
for them to, okay, that happened next week, we'll start releasing now or keep water now, so a week. Yeah.
Mhm.
but I guess the question is, so you've got this now optimized discharges, right? But it's almost like, can you extract from the optimized discharges the rule set that would be used in order to make those decisions? So we're going the other direction. Right now, the rules that go, it's like, if the water level is this and it's summertime, then discharge only that, right? And so you're saying, well, you can do better than that
Yes,
as far as the outcome, which is the load to the estuaries, but can you take your outcome and reverse engineer the rules?
I see, but I believe we can because it like depends on water levels and those, but you have to measure those parameters like phytoplankton, nitrate and phosphorus. So I believe we can do that, yeah.
Got another question. You said that the one solution to the algae bloom problem was discharging water, because presumably then the algae go out with the water.
It means the other way. So here, like the lake is already for our case studies, the lake is already like contains algae, then they discharge water with algae.
Yes.
To the estuary, so we thought, okay, let's keep it in the lake, it's pollutant in a way, and then release in times where water is better quality.
I see, so the water will come back. So
Yeah. My hypothesis.
Well, no, the algae goes, the idea is that, you know, this minimization is like trying, you know, the lake is. Optimizing how to manage the lake for its own water quality is another question. The question is now the lake has this water quality based on the inflows and the seasonality of photosynthetic growth. How do you manage it such that it's discharging the least?
Yes,
But you also been working on projects to optimize the watershed, the Pacific watershed,
Yeah,
land use
yeah.
to reduce overall
Yeah.
loading, which would have an effect on.
another. The lake itself, there are other ways to improve water quality.
Mhm.
Focusing on inputs to the lake.
How about this water level thing? So all LOSUM, like the new current operation and all of your optimal scenarios, maintain the water, I don't know, a foot or two above the ecological envelope,
Yeah,
which of course reduces discharge, but you know, there are other potentially like direct effects like SAV dieback, which
Yeah.
can cause more flocculent sediment, which can be wind distributed and cause fire, you know, all those processes are not in the model, right? I mean, you do have wind.
no, they are not.
Yeah,
We have wind, but we do not have those
ecological.
ecological features.
So,
That's the water level.
so what are the ramifications of managing a lake at a higher one?
Yeah. That's the psychology.
Yeah, I don't know, is that I mean, is that a trade-off that they're talking about? You know, wading bird habitat, apple snails, the littoral, you know, wetlands and everything.
I would believe that like, that's also like average year, it's like just following the operation, which they do not follow usually, so maybe they can like, if they wanna like follow those ecological targets that will release more water than it's already there in the operations.
I mean, could you adapt your optimization scheme so that ecological envelope was first and then the others would,
Can.
yeah, see what it would take? What would be the collateral damage to maintain the ecological envelope?
Yeah, I believe like will not reduce all of those those. It might be acceptable because those like operation like very good like for 7 and 8%. So maybe like we can accept less reduction than that.
To a
Do
moderate
some,
job at the
yeah.
envelope.
Oh, that's not the scope of this one. So, chlorophyll A in Okeechobee, I don't know if I've heard this before, but it's a proxy for a few different species of blue-green algae that actually exist in Okeechobee, right? Like it's not, is it just the weird buildup of algae that you saw along the boats? That's the predominant algae species that I assume you're trying to optimize for? Or is there a few different ones that are like,
No, so yeah, like I'm not very into algae, right? So yeah, I use like this dominant cyanobacteria
okay.
of the blue algae as like the indicator. Then I use like chlorophyll A, it's like indicator of vitamin. So yeah, like I did not get into details into the algae.
That's good. That's how it's going.
Let's get another round of applause. Thank you, Asana. Okay, a couple of announcements about class. So next week we have a virtual seminar. We have Dr. Robert Nairn. He is going to be presenting, well, he's from Oklahoma, so I don't think he's coming, but I'll let you know. And he's going to be talking about working with Mother Nature to address ecotoxic metals and restore streams. And then just a couple of announcements. So if you're in the environmental engineering section, I've graded several of your abstracts. I'm like almost up to date. One thing I'm noticing is that we define like what an abstract does. It reviews like what's the problem, what did they do to find some information, like what were the results and what were the ramifications. So a lot of them are great. And then there's this this consistent comment I have to give, which is what are the broader implications? So sometimes you just end and be like, and it was, treatment A was higher than treatment B, and you just stop. And I'm like, okay. Then you have to write something like, these findings will be relevant for advancing the future of blah, blah. You have to like tie it to the societal outcomes. And the second is that I'm getting like 5 sentences and they're not integrated into a paragraph. An abstract is an integrated whole rather than, honestly, just like put them together and see if they flow. You're probably there, right? So those are the 2 major comments. Any questions about logistics of class? All right, well then, one more round of applause. Thank you, Asana. We'll see you again next week.